Infinite matters. Nothing lasts forever except in infinite time. Nothing goes on forever except in infinite space. No infinite number is as big as infinitely large number. If we're going to allow infinitely to muscle its way into our case to find the biggest number in the world, that may seem like cheating because all the numbers we've talked about so far, however vast they may be, are infinite. They all lie at specific points on the real number line. He could find a he could he how could a finite number, however big it is, compete with something that's infinitely big? For the moment, though, that's not the point. Strange to say, in order to reach finite numbers to even greater size than those we've so far encountered, we need to enlist the help of the infinite. Infinitely a slippery concept. We can probably grasp it in our minds because our minds are finite, capable only of finite thoughts, yet we recognize that infinity might exist in the real world. Cosmologists debate whatever the universe is limited in time and space or whether it goes on forever. Current observations suggest the latter, that it may be infinite in extent and duration. But we don't yet enough information to know for sure. We also don't know what happened before the Big Bang, the instant at which all the contents of the universe began the outward rush from a state of incredibly high density and pressure. Was there before? And if there wasn't, how could the universe have made the transition from the state of non-existence outside of time to something that was tangible and temporal in nature? Physical infinities, in the form of infinitely large space and times, or infinitely high densities and temperatures, are concepts we can discuss but never truly grasp. The same is true of the infinite in mathematics. We can talk about we can talk about the number line going on forever without reaching an end, yet have no meaningful sense of what infinitely long number long number line would be like. Until the latter part of the 19th century, philosophers and mathematicians drew a sub-distinction between what Aristotle, a couple of thousand years earlier, had called potential and actual infinity. There's only illimitable potentiality of addition, he said, and illimitable potentiality of division, for it will always be possible to find something beyond the total. Most mathematicians were happy to accept the notion of potential infinity in terms of the number line. For instance, they recognized that there was no point at which it abruptly stopped at that, and that however you travel along it, there would always be more numbers beyond. By the same token, it was known that irrational numbers, such as pi and the square root of 2, had decimal expansions that never ended nor repeated in any predictable number and any predict in any predictable pattern. But there was still a reluctance to accept infinity in its entirety as a fully formed thing in itself, and not merely an interminable extension of the finite. Mathematicians refused, or simply did not know, how to deal with actual infinity. They were aware of it hovering how over the subject like a threatening could be co- storm could they were aware of it hovering over the subject like a threatening storm cloud, but turned a blind eye to it. Even Carl Gauss, colossus of mathematicians, that he was expressed in 1831, his horror of the actual infinitude. I protest against the use of infinity magnitude as something, as something completed, which which is never permissible in mathematics. Infinity is merely a way of speaking, the true meaning being a limit with certain ratios approach indefinite recurrence, while others are permitted to increase without restriction. This state of denial didn't prevent mathematicians from developing key concepts such as infinite series, limits, and infinitesimals by, for instance, letting n to infinity. Isaac Newton and Gottfried Leibniz independently were able to lay the foundation of calculus without having to grant that infinity was a new type of mathematical object. But in retrospect, it it's clear that something eventually had to give. Even the dawn of the 17th century, certain paradoxes and puzzles had arisen, which suggested that actual infinity wasn't an issue that could be brushed aside forever. These conundrums stem from the observation that it's possible to pair off all the members of an equation of objects with all those of order of equal size, leaving none left over. Applied to indefinitely large collections, this pairing of principles seems to fly in the face of a common sense idea first expressed by Euclid, namely that the whole is always greater than any of its parts. For instance, it appeared that all the positive integers could be paired off with only those that are even, with 1 with 2, 2 with 4, 3 with 6, and so on, despite the fact that positive integers also include odd numbers. Galileo, in considering such problem, was the first to show a more enlightened attitude towards the infinite, where he said, "Infinity should obey a different arithmetic than infinite numbers." What kind of different arithmetic could it be? And how could something as bizarre as infinity, endlessness fully realized in the moment, have a place in mathematics? Potential infinity, regarded as the limit of an eternal case, was by contrast a comfortable notion, and Aristotle pointed out was reflected in the unending cycle of the seasons of the apparent limitless indivisibility of a nugget of gold, the system of atoms being the unknown. The concept of potential infinity lulls us into thinking that if we just keep going for enough or long enough, we'll get closer to infinity. Is then only a small step to popular wit that infinity is just like a very big number, and that a trillion is somehow closer to infinity than says say than say that is or 1,000. But, but this simply isn't the case. Traveling further down the number line or counting to bigger and bigger numbers gets us no nearer whatsoever to infinity. We're just as far from or close to infinity at the number one as we are at, at any infinite number we care to name. However, was put another way, all of infinity is contained between any two numbers, no matter how close they are. So that setting off down the road to larger and larger numbers in search of infinity is utterly futile. The fact that is that infinity exists between 0 and 1, for instance, because there are infinitely many variations, 1 over 2, 1 over 3, 1 over 4, and so on. Infinity is not like a big finite number at all. To deal with infinity, we have to jump out of the realm of finite numbers altogether and stop using them as a crutch to our understanding. The German mathematician David Hilbert conjured up a striking mental picture to illustrate how strange the arithmetic of infinity can be. Imagine, he said in a lecture given in 1924, a hotel with an infinite number of rooms, unlike, unlike an ordinary number, which can accommodate any more guests once all in its room are occupied. Hilbert's Grand Hotel can always find more space. If a new guest arrives, all the manager has to do is ask everyone currently in residence to move into next higher room number. For the guest in room 1 relocates to room 2, the coupon of room 2 to 3, and so down the corridors and floors, the stretch and away forever, so that the newcomer can be placed in room 1. 1,000 new guests could arrive and not be disappointed. All current residents would be simply asked to switch to their room number that was then 1,000 higher. No one need ever be turned away. Even if an infinite number of people suddenly arrive unannounced, every single one could be accommodated by moving the coupons of rooms 1, 2, 3 and so on to rooms 2, 4, 6, etc. Thus freeing up all the infinitely many odd number rooms. This more capacious of hotel need never turn anyone away. Even if an infinite number of coaches were to arrive on morning, it's carrying an infinite number of passengers. Hilbert's Hotel is a weird and wonderful place that doesn't fit comfortably with any of our common sense notions of how the world works. But common sense isn't much used in dealing with infinity. The fact is, properties of infinitely many things are fundamentally different from those of infinitely many things. It may be hard to swallow, but when it comes to Hilbert's Hotel, the statements "there's a guest in every room" and "more guests can be accommodated" aren't mutually exclusive. Whenever a revolution starts to brew, whether in science or mathematics, intellectual battle lines are drawn between the old guard and the new. Controversy erupted over Einstein's theories of relativity, and slightly earlier, at the dawn of the 20th century, where the suggestion began to circulate that energy might be quantized. In the late 19th century, mathematicians faced a crisis of their own. Were they ready to accept that actual infinity was a mathematical object? The majority, aligning themselves behind Aristotle, Gauss, and other gods who in the past would tolerate only potential infinity, were not. Only a handful of theorists were prepared to wave the banner for change, to build the foundations of an entirely new branch of mathematics, set theory. At the forefront of this revolution were three German mathematicians: Richard the Deakin, Karl Weierstrass, and head and shoulders above the others, Georg Cantor. Set theory, and with it the concept of infinite sets, burst upon the mathematical scene with the publication of a single paper by Cantor in 1874 titled "On the Property of the Collection of All Real Algebraic Numbers." Cantor realized that the age-old pairing of method used to tell if two finite sets are equal could be applied just as well to infinite series. It followed that there really are just as many even positive integers as there are positive integers altogether. Far from being a paradox, Cantor showed that this, in fact, was a defining property of infinite series, that the whole is no bigger than sum of its parts. He went on to show that the set of all numbers not that he went on to show that the set of all natural numbers n, which is the set of all non-negative integers 0, 1, 2, 3, sometimes 0, is not included. contains precisely as many members as the set of all rational numbers Q numbers that can be written in the form of one whole number divided by another. He called this infinite number aleph-null, aleph being the first letter of the Hebrew alphabet and null the German for zero. It's also known as aleph zero of aleph-null. You might be wondering why call it aleph-null and not just aleph, because surely there can be only one kind of infinity. Well, first of all, aleph-null isn't infinity because infinity is a broad philosophical concept, not precise mathematical thing. Aleph-null is the size of the infinite set of natural numbers. It's what referred to as a transfinite number because it transcends the size of any infinite number. Second, surprisingly, some infinite sets are bigger than aleph-null. In fact, aleph-null is the smallest transfinite number, even though it's infinitely large. How can this point be? The natural numbers go on forever. What could it possibly mean to say that some sets of numbers go on forever and then some? Again, it's important to be mathematically precisely and not try to conjure up some fetch mental image of what different types of infinity might be like. Cantor was able to show that the size of the sets of all natural numbers and all integers and irrational numbers was the same and equal to aleph-null. Bigger than aleph-null is aleph-1, which will define the later in the chapter. According to what's known as the continuum hypothesis, aleph-1 is the size of the set of all real numbers R, which includes both rational and irrational numbers. The continuum hypothesis may or may not be true depending on which version of set theory you're working with. Something else we'll come back to later. But for now, thinking of aleph-1 as the size of the real number set is useful because it illustrates how one transfinite number can be bigger than another. On the real line, irrational numbers such as square root of 2 are infinitely more dense or common than are rational numbers, so that the set of all real numbers is infinitely larger than the set of rational or natural numbers. The hierarchy of alephs doesn't stop at aleph-1. There's also aleph-2, aleph-3, and so on, each infinitely bigger than the one before. The fact there are infinitely many different alephs. Not only that, but corresponding to each aleph, it turns out are infinitely many other infinitely large numbers. To understand this, we have to explore the important difference in the realm of transfinite numbers between cardinals and ordinals. In everyday language and arithmetic, cardinal numbers tells us how many there are in a collection of things 1, 6, 57, and so on, whereas ordinal numbers, as the name suggests, give the order of position of something first, 6, 57, and etc. As far as ordinary situations are concerned, then there's not much difference between cardinals and ordinals, and any difference there seems pretty obvious. Say, we're talking about matches. It's clear that you can have a 6 match without having at least 6 matches in the group, that you could still have a 6 match even if there were 8 in a group. You could also have 6 matches without having a 6-1 of if you didn't put them in any particular order. say, by just making a pie of them. But these middle distinctions aside, we can use the same symbols for cardinals and ordinals, 1 or first, 6 or sixth, and 57 as 57th, and so on, and not worry too much over, over how they differ. When it comes to infinite sets of numbers, however, the distinction between cardinals and ordinals become vitally important. To understand why, we need to look at the basics of set theory, the powerful new branch of mathematics that Cantor, along with Dedekind, were instrumental in developing. Informally, a set in maths is like any other kind of set, such as a collection of stamps or vinyl records, just as grouping of objects. It describes the listing its members or elements separable commas within braces. For example, are both sets. The size of the set, how many members and elements it contains, is known, and its cardinality is given by a cardinal number. But the sets just mentioned have 4 elements and so have a cardinality of 4. In general, the cardinality of two sets is the same if every number in the first set can be paired off with one in the second so that nothing is left over. In other words, they have a one-to-one correspondence. For example, we can pair 1 with cat, 8 with tea, 64 with apple, and 125 with tree to show that these sets have the same cardinality. The finite cardinals, the cardinals that measure the size of the finite sets, are just the natural numbers 0, 1, 2, 3, and so on. In the case of finite sets, the difference between the size of a set given by a cardinal number and its length given by ordinal number is so slight as to be almost pedantic. But when but when it comes to infinite series, Cantor realized these are two very different things. To grasp how different they are, we need to understand the idea of well-ordered set. A set is considered to be well-ordered if each subset or subgrouping of its members has a finite member, provided that this subset isn't empty. The finite set, for instance, is well-ordered. The set of all integers, on the other hand, which includes all negative whole members as well as positive ones, isn't well-ordered because there is no first number. The set of all numbers is well-ordered because despite having no specified member at the end, it has one at the start, and every subset containing only natural numbers also has a first member. Now, key point is that while ordered infinite sets of the same size or cardinality can have different lengths, that isn't an easy concept to grasp even for a mathematician. Strictly speaking, we should say different ordinalities rather than lengths, but the more familiar terms helps us to appreciate what's going on. Think about the well-ordered sets. When the three dots means carry on forever. Both sets contain all the natural numbers and therefore have the same size of cardinality, aleph-null, but the second is slightly longer. At first, this doesn't seem to make sense. After all, if we were talking about finite sets, then it's obvious that are identical in length because they both contain first members. But infinite sets are fiendishly counterintuitive. The set has no finite end member because the three dots tell you to carry on forever without stopping. However, it's different. It contains a sequence of members that carries on forever. However, it also contains one member that is beyond all the members on the never-ending sequence that has been detached. It with 3 taken out, the sequence is just long as. In other words, you could back off the members of these 2 sequences and never have one left over. By moving the 3 to the end, so that it comes after the infinite sequence adds 1 to the length. Think of it another way. When the first set, there's first element 0, second element 1, a third element 2, a fourth element 3, and so on. With the second, there's also a first, second, third, fourth, etc. However, there's one element 3 that is none of this. The ordinal is assigned to 3, not the value of the number, but the order in which it appears. It is greater than anything that comes before it. We need a naming system for this class of infinite numbers, which is different from the alephs. Mathematicians call the smallest infinite ordinals. Mathematicians call the smallest infinite ordinal the shortest length of the set of all natural numbers, omega. The ordinality of the set, where 3 is placed after all the other natural numbers, is 1 greater, namely omega plus 1. Another way of saying this is that 3 is the omega plus 1 element in the set of. The plus sign here is a bit misleading because it doesn't mean addition in the usual sense, but rather that omega plus 1 is the next ordinal after omega. Ordinal subtraction also works very differently from the way we are used to taking away. The ordinality of with 3 taken out is still omega. For instance, if we want to compute omega minus 3, we can simply remove elements from the end of the set of all natural numbers, since there isn't an end. Instead, we remove elements from the start, but in doing so, we find that omega minus 3 is just omega again. The fact is that the length of the set of natural numbers can be reduced. No matter how large the infinite number of elements is removed from it. On the other hand, its length can be increased by putting the elements that have been removed at the end. To recap, aleph-null and omega both refer to the same set, the set of natural numbers. Aleph-null is its size, how many elements it contains, and omega is its shortest length. This length can be increased by taking elements out of their unusual order and placing them at the end. The set, for instance, has a cardinality of aleph-null but an ordinality of omega plus 2. We can keep on increasing the keep of the set of natural numbers by moving more and more elements beyond the 3 dots that mean carry on forever. Omega plus 3, omega plus 4, all the way up to omega plus omega or omega times 2, which could be written, for instance, as the subset of all even numbers followed by subset of all odd numbers. Even since each of these is equal in length to omega, then we can continue as before by shifting elements to the end. For instance, one way to write is then we can move on to the power of omega, such as all the way up to omega to the power of omega, then to stack of the powers power towers of omega, stretching higher and higher until we reach a power tower of omegas that is omega's height. At this point, we reach a new level, an ordinal that Cantor can call epsilon 0, just as omega is the smallest ordinal that lies beyond the infinite ordinals. Epsilon 0 is the smallest ordinal that lies beyond any ordinal that can be expressed in terms of omega using addition, multiplication, and exponentiation. Is the gateway to the realm of epsilon numbers, which like that of the omega ordinals is infinitely large. The whole process described for the omegas can be repeated for the epsilons until the mathematical operations that are possible using epsilons, including power towers of epsilons or even epsilons of epsilons, are exhausted. At this point, we arrive at yet another level of finite ordinals, starting with zeta 0, and so it goes on and on and on.
More than anything, the difficulty in progressing further is one of notation. Eventually, all the Greek letters are exhausted, along with any other ordinary labeling system to represent the hierarchy of infinite ordinals that stretches it away into the distance, compounded with the problem of finding more powerful and compact means of notating fast infinite ordinals is a mounting degree of technical difficulty. Some milestones named after the mathematicians with whose work they are associated lie along the way. Once zeta 0 has been left far behind. The Pfeffermans could suit the ordinal, the small and the large Veblen ordinals, both of which are outrageously large. The Bachmann-Howard ordinal and the Church-Kleene ordinal, first described by the American mathematician Alonzo Church and his student Stephen Kleene. To describe properly what any of this mean will take a book in itself. So esoteric is the math behind them. The church clinic ordinal, for instance, is so incomprehensibly vast that there's no notation whatsoever then can, that can reach up to it. The ordinals are rarely encountered by professional mathematicians, let alone the wider public, but the essential point about them all is just they are countable. In other words, all the infinite ordinals we've talked about so far, starting with omega, can be paired off one to one, leaving none left over with the natural numbers. Another way of saying this is that they all correspondent to the cardinality aleph-null. We're now nearer to a bigger kind of infinity when we get to epsilon 0 or even the mighty Church-Kleene ordinal that when we can start it. Colossal too they may be, they may represent different ways of ordering the set of all natural numbers. A bigger kind of infinity means one that transcends aleph-null altogether. But how is that possible? Aleph-null doesn't behave like the numbers we're used to dealing with, whereas 1 plus 1, aleph-null plus 1 is still aleph-null. Aleph-null plus an infinite number or minus an infinite number is still aleph-null. This suggests a new twist to the song 10 green bottles, along the lines of aleph-null green bottles hanging on the wall. Aleph-null green bottles hanging on the wall, and if one green bottle should accidentally fall, there there be aleph-null green bottles hanging on the wall. Repeat ad infinitum. You can change aleph-null by subtracting from it, adding to it, or multiplying it by an infinite number, or even multiplying it by aleph-null itself. But Cantor showed, using a theorem that's now named after him, that there is a hierarchy of infinites of which aleph-null is the smallest. The next infinite cardinals, the next infinite cardinal aleph-1 is much bigger and equal in its size to the set of all uncountable ordinals, namely those those with cardinality of the aleph-null. Because the natural numbers are countable, aleph-0, the size of the set of natural numbers, is said to be a countably infinite cardinal. Corresponding with it is the smallest infinite countable ordinal, omega, and infinitely many other countable infinite ordinals. All of these infinitely many countable ordinals arise because in the case of ordinals, information on order matters, so that a much finer distinction had to be made than with cardinals. Even so, all the countable ordinals from omega onwards, including the epsilon numbers and the rest, fall within the same cardinality of aleph-null. With aleph-1 comes a dramatic change. Not only is aleph-1 indescribably larger than aleph-null, but is also uncountable. Corresponding to it is the smallest uncountable ordinal, omega-1. We said that we've said that aleph-1 is the size of the set of countable ordinals, but does it have any other interpretation? Aleph-null measures the size of the set of all natural numbers. Does aleph-1 also correspond with anything that's familiar and conceptually easy to grasp? Cantor thought so. He believed that aleph-1 was identical with the total number of points on a mathematical line, which, astonishingly, he found was the same as the number of points on a plane or in any higher n-dimensional space. This infinity of spatial points, known as the power of the continuum C, is also the set of all real numbers, all rational numbers plus irrational numbers. Cantor's continuum hypothesis asserts that C equals aleph-1, which is equivalent to saying that there is no infinite set with a cardinality between that of the natural numbers and that of the real numbers. Yet, despite much effort, Cantor was never able to prove or disprove his continuum hypothesis. We now know why, and it strikes to the very conditions of mathematics.
In the 1930s, Austrian born logician Kurt Gödel showed that it's impossible to prove the continuum hypothesis is wrong, starting out from the standard axioms or assumptions of set theory. 3 decades later, the American mathematician Paul Cohen showed that neither can it be proved correct from those same axioms. Its status was, in other words, indeterminate within the normal framework that mathematicians used. Such a situation had been on the cards ever since the emergence of a famous theorem discovered by Gödel called the incompleteness theorem. But the independence of the continuum hypothesis was still uncertain because it was the first concrete example of an important question that probably couldn't be decided either way from the universally accepted system of axioms on which most of mathematics is built. The debate about whether the continuum hypothesis is ultimately true or not, or whether it's even a meaningful statement, rumbles on among mathematicians and philosophers. As for the nature of the various types of infinites and the very existence of infinite sets, this depends crucially on what number theory is being used. Different axioms and rules lead to different answers to the question what lies beyond all the integers. This can make it difficult or even meaningless to compare the various types of infinities that arise and to determine the relative size. Although within any given number system, the infinites can usually be put into a clear order. There is a towering hierarchy of cardinals beyond aleph-null, assuming the continuum hypothesis to be true, which is the default position of most mathematicians because it has helpful consequences. The next cardinal is aleph-1, equal to the size of the set of all real numbers. After this comes aleph-2, then aleph-3, and so on without end. To each aleph corresponds an infinite number of ordinals, the smallest of which is omega in the case of aleph-null, omega 1 is in the case of aleph-1, omega 2 in the case of aleph-2, and so on. Are any of these mathematical infinities enacted in the real world, or are they pure abstractions? Or are they pure abstractions? We saw earlier the cosmologists are leaning towards the view that the universe we live in is geometrically flat and endless in space and time, and if thus go on forever, with which kind of mathematical infinity does it correspond? The fact that space and time appear to come in discrete amounts, the Planck length and Planck time means that they are not continuous like the points of a mathematical line. So if the actual universe is infinitely large, it seems that it could correspond with only the smallest kind of infinity, aleph-null, and anything bigger might always be confined to our intellects or some platonic space unfettered by the laws of physics.